I want to start by telling you about a kind of motion that, when you really stop and think about it, becomes one of the most disorienting realizations in all of astrophysics. Right now, as you're sitting, wherever you're sitting, listening to my voice or watching this video, you feel perfectly still. The chair beneath you isn't moving. The floor isn't shifting. The room around you, by every measure your senses can provide, is rock solid and absolutely stationary. But you are not still. You are not even close to still. Let me walk you through the layers of motion that you're participating in right at this moment, whether you know it or not. First, the Earth is spinning on its axis. At the equator, that spin carries you eastward at about 1,000 miles per hour. If you're at higher latitudes, like most viewers, the speed is somewhat less, but it's still substantial. So already, just standing in your kitchen, you are hurtling through space faster than a commercial jet. Now layer on top of that the orbital motion of the Earth around the Sunday. We move around our local star at about 67,000 miles per hour. That's roughly 30 kilometers every second. Every time you take a breath, in the space of that breath, you and everyone you know has traveled, about 120 miles around the Sunday. The Earth isn't just spinning, it's racing. But the Sun itself is in motion. Our entire solar system, all the planets and asteroids and comets, the entire grand orchestra of bodies orbiting our star is being carried around the center of the Milky Way at about 514,000 miles per hour, 230 kilometers per second. We're falling into a great galactic orbit, completing one circuit around the supermassive black hole at the heart of our galaxy every 225 million years. The last time the Sun was in this exact position in its galactic orbit, dinosaurs had only just begun to dominate the planet. So now we've got the Earth spinning, the Earth orbiting the Sun, the solar system orbiting the galactic center, and you might think, well, surely that's where the motion ends. The galaxy itself is, the big stable platform on which all this motion happens. The Milky Way is the stage. It doesn't move. But here's the thing. The Milky Way is moving too. And not just moving in some random direction, drifting aimlessly through the void. The Milky Way is being pulled by something, pulled toward a specific location in the universe, pulled at a speed that is, frankly, almost incomprehensible. We are, right now, the entire galaxy, every star you can see in the night sky and the 100 billion stars you cannot see, hurtling through intergalactic space at about 1.3 million miles per hour, 600 kilometers every second. And the truly remarkable thing, the thing that I think genuinely deserves your attention, is that we don't fully know what's pulling us. We can measure the motion. We can chart its direction. We can map the destination toward which the entire Milky Way is being drawn. But when we point our most powerful telescopes at that destination, when we try to identify the source of the pull, we cannot see what it is. That's the title of this discussion. Of course, we can't see what it is. And I want you to sit with that for a moment, because it's a genuinely astonishing situation. There is something out there, something so massive that it can drag along not just our galaxy, but a vast collection of galaxies surrounding us, something whose gravitational influence reaches across hundreds of millions of light years of space, and we cannot directly see it. How is that possible? How can the universe contain such a colossal influence and yet hide it from view? And what exactly might be sitting there in the dark, pulling on us, drawing us inexorably across the cosmos toward a rendezvous we cannot yet visualize? This is the puzzle that astronomers have been wrestling with for nearly half a century now. It has a name. It's called, evocatively, the Great Attractor. And the story of how we discovered it of how we've tried to understand it and of how it continues to defy our complete comprehension is one of the most fascinating in modern cosmology. Now, to appreciate just how strange this puzzle is, I need to take you back just briefly to the foundational discovery that changed our understanding of the universe. Because for most of human history, we thought we lived in a static, eternal cosmos. The stars were fixed points, the heavens were unchanging. Whatever motion existed in the universe was confined to the planets in our own solar system, which we knew danced in their own ways around the Sunday. But in the 1920s, an astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, made a discovery that overturned this entire picture. Hubble was looking at distant galaxies, and he noticed something extraordinary. The light from those galaxies was shifted toward the red end of the spectrum. Now, this redshift, as we call it, was a signature that the galaxies were moving away from us. And not just some of them, all of them. Every galaxy Hubble could measure, with the exception of a handful of very nearby ones, was receding, moving away, fleeing from our position in the cosmos. And here's the truly remarkable thing. The farther away a galaxy was, the faster it was fleeing. There was a beautiful linear relationship between distance and recession velocity. Double the distance, double the speed of retreat, triple the distance, triple the speed. This was the signature, the unmistakable fingerprint of an expanding universe. The cosmos itself was getting bigger. The space between galaxies was, literally stretching, carrying the galaxies along with it like raisins in a rising loaf of bread. This discovery was profound. It told us that the universe had a beginning. It told us that there was a moment billions of years ago when everything we now see was compressed into a much smaller volume. It told us, in essence, about the Big Bang. But for our story today, the most important thing about the expanding universe is that it gave us a backdrop against which to measure local motion. If every galaxy is moving away from us at a speed proportional to its distance, then any deviation from that pattern, any galaxy that's moving faster or slower than it should, must be due to some additional local influence. Some gravitational pull from nearby mass, some attraction that's tugging it away from the smooth cosmic expansion. And so, by the 1970s, astronomers had begun to systematically catalog these deviations. They mapped the motions of nearby galaxies, looking for patterns, and what they found when they really started to look carefully was remarkable. The galaxies in our region of the universe were not flowing smoothly outward in accordance with the simple Hubble expansion. They were drifting. They were being pulled. And they were all being pulled more or less in the same direction, a particular direction in the sky, a direction that pointed towards something specific in the constellations Centaurus and Hydra in the southern sky. The pull wasn't subtle. The Milky Way and every galaxy in our immediate cosmic neighborhood was moving at about 600 kilometers per second relative to the cosmic microwave background relative, that is, to the smooth blanket of radiation left over from the Big Bang that fills all of space, 600 kilometers per second, all of us heading in the same direction, like a great cosmic stampede. What was pulling us? This is where things start to get really interesting. Because when astronomers tried to identify the source of the pull, they ran into a problem. A problem that, in retrospect, makes the whole story almost poetically frustrating. The direction in which we're moving, the direction toward which the Great Attractor pulls us, lies in a part of the sky that, from our position inside the Milky Way, is partially obscured by what? By the disk of our own galaxy, by the dust and stars and gas that make up the very band of light we call, in our most romantic moments, the Milky Way. You see, our solar system sits inside the disk of our galaxy. We are embedded in it. When we look up at the night sky, the Milky Way appears as a band stretching from horizon to horizon because we are looking sideways through the disk. And just like trying to see through a forest by looking sideways through the trees, looking through the disk of our galaxy is extremely difficult. The light from objects on the other side gets absorbed, scattered, dimmed by the intervening dust and gas. There's a region of the sky encompassing about 20% of the entire celestial sphere where our view of the universe beyond is significantly obscured. We call this region the zone of avoidance. And in one of those cosmic coincidences that seem almost designed to taunt us, the Great Attractor sits right behind the zone of avoidance, right in the part of the sky that we cannot easily see. The most mysterious gravitational influence on our entire galaxy lies hidden behind the foreground of our own galactic disk. You see why I find this so wonderful? It's as if the universe is playing a kind of cosmic hide and seek with us. The thing we most want to understand, the thing pulling our entire civilization through space, is hidden behind the very galaxy we live in. It's the kind of irony that, only nature can come up with. Now, the existence of the zone of avoidance doesn't make the Great Attractor completely invisible. Far from it. Astronomers have been working for decades to peer through the obscuration using techniques that don't rely on visible light. X-ray telescopes can see through some of the dust. Radio telescopes can pick up the signatures of galaxies that would otherwise be hidden. Infrared observations can penetrate the dust quite effectively because longer wavelengths of light scatter less than visible wavelengths. And so, slowly, painfully, with enormous effort, we have begun to map what lies behind the zone of avoidance. And what we found when we first looked was, well, somewhat puzzling. We found a region called the Norma Cluster, a substantial cluster of galaxies sitting about 220 million light years away from us, right at approximately the position we'd expect the Great Attractor to be. The Norma Cluster is real. It contains thousands of galaxies. It has a lot of mass. But here's the problem. Even with all the mass we could account for in the Norma Cluster and the surrounding region, the gravitational pull simply wasn't enough. The numbers didn't work out. The combined mass of all the visible galaxies in that direction was not sufficient to explain the speed at which our entire galactic neighborhood is being drawn that way. Something else was needed, something more massive, something that, again, we couldn't see. So what could it be? In the late 1990s and early 2000s, as our maps of the local universe got better and better, an even more remarkable discovery emerged. The pull on our galaxy, it turned out, was not just coming from the immediate region around the Norma Cluster. The pull was coming from much, much farther away, from a structure that lay beyond the Great Attractor itself, on the far side, hundreds of millions of light years from us. A structure that we could just barely glimpse, but that, when we did glimpse it, revealed itself to be one of the most massive concentrations of matter known anywhere in the observable universe. We called it the Shapley supercluster, and I want to take a moment to convey just how staggering this object is. A supercluster is, in the hierarchy of cosmic structure, the largest gravitationally bound assemblage of galaxies. Galaxies grouped together into clusters. Clusters grouped together into superclusters. And the Shapley supercluster is, by most measures, the most massive supercluster within several hundred million light years of us. It contains something on the order of 40 major galaxy clusters, more than 8,000 individual galaxies, and a total mass equivalent to about 10 million billion suns, 10 quadrillion solar masses. The sheer scale of it is, frankly, hard to wrap your mind around. And this enormous concentration of matter, sitting about 650 million light years from us, is pulling on our entire local neighborhood. Pulling on the Milky Way, on Andromeda, on every galaxy within hundreds of millions of light years of us. The Great Attractor, when astronomers first identified it, was largely the gravitational halfway house on the path to Shapley. We weren't being pulled toward one thing. We were being pulled towards something that was itself being pulled towards something even bigger. This realization, this layered structure of cosmic gravity, was a revelation. It transformed our understanding of how mass is distributed in the universe. The cosmos is not, as we once thought, a relatively uniform distribution of galaxies with some local clustering. It is, at the largest scales, a dramatically inhomogeneous landscape with vast regions of relative emptiness punctuated by colossal concentrations of mass. And our galaxy is right now falling through this landscape, drawn toward one of the great concentrations. So you might think, well, we've solved the puzzle. The Great Attractor is the Norma cluster, and the deeper pull is the Shapley supercluster, and that's the answer. We know what's pulling us. Mystery resolved. But that's where the story takes a genuinely strange turn. Because in the years since these structures were identified, we've kept measuring more carefully. We've kept refining our maps. And we've discovered that the pull on the Milky Way is not perfectly aligned with the Shapley supercluster. The pull is in a slightly different direction. And the magnitude is, in some measurements, larger than even the Shapley supercluster can account for. There's still mass we can't see. There's still influence we can't explain. There's still, in the deepest sense, something out there that we don't yet understand. And it's that residual mystery, that lingering question, that I want to spend the rest of this video exploring with you. Because the implications, when you really think them through, are profound. Profound enough that when astronomers really sit and contemplate what the data is telling us, there's a certain edge to their conversations. Not a fear in the dramatic Hollywood sense, but a kind of disquiet. A recognition that we are participants in a cosmic process that we do not fully understand, being pulled toward a destination we cannot fully see. I want to take you, in just a moment, through what we know about this destination, what we can infer about its size, its mass, and its character. I want to tell you about a much larger structure, identified only in the last decade, that gives our cosmic motion a kind of context that previous generations of astronomers could not have imagined. And I want to take you to the very deepest question of all, which is, what does it mean that we are, in the truest sense, moving through the universe, falling toward an unseen rendezvous? Because here's what I want you to understand. The motion is real. The pull is real. The destination, whatever it ultimately turns out to be, is real. And the fact that we can measure all of this, that human beings on a small planet can deduce the speed and direction of their galaxy's motion through the cosmos by carefully observing the patterns in the night sky, is, one of the most remarkable triumphs of the human intellect. In just a few thousand years, we have gone from believing that the Earth was the center of a static cosmos to mapping the gravitational pull on our entire galaxy from invisible structures hundreds of millions of light years away. We have gone from thinking the heavens were unchanging to discovering that we are participants in a great cosmic flow, drawn by forces we are only beginning to understand. That's a kind of progress that, when you stop and think about it, ought to fill you with a sense of wonder. But the wonder, I want to suggest, is not just in what we've discovered. The wonder is also in what we haven't discovered. The wonder is in the questions that remain open. The wonder is in the fact that despite our most powerful telescopes and our most sophisticated analyses, the universe is still telling us, gently but firmly, that we don't have the whole picture yet. There is more out there. There is more being hidden. There is more pulling on us than we can directly perceive. And the deepest implication, I think, is this. If our galaxy is being pulled by something we cannot see, if our entire cosmic neighborhood is participating in a flow whose source remains partially mysterious, then we are reminded, in the most concrete possible way, of how much of the universe lies beyond our direct observation. The visible universe, the stars and galaxies and structures we can map with our telescopes, is, in some sense, only the surface of a much deeper reality. Beneath the surface, behind the obscuration, beyond the zone of avoidance, there is more, always more. What is this more? What is the actual nature of the force drawing the Milky Way across the cosmos? Is it just ordinary matter, hidden by dust and distance, that we will eventually identify with better telescopes? Or is it something stranger? Could it be related to the dark matter that we know permeates the universe, that vast invisible substance that makes up most of the matter in every galaxy? Could there be entire structures of dark matter, gravitationally significant but completely invisible to our light-based observations, that are responsible for the pull on the Milky Way? These are the questions I want to explore with you. Because you see, when we really start to investigate the nature of the Great Attractor, we run into the larger mystery of dark matter itself, and through that, into one of the deepest puzzles in all of modern physics. Now, here's what I find truly arresting about the situation we're in. We have measured the motion of our galaxy with extraordinary precision. We know, to within a few percent, the speed at which we're traveling and the direction we're heading. We have, in a real sense, established our trajectory through the cosmos. We are like sailors on a ship who know their heading and their velocity perfectly well, but we cannot see the destination. We cannot see the harbor. We cannot see what's drawing us across the dark waters. And we're not, going to arrive anytime soon. The timescales for cosmic motion are so vast that even at 600 kilometers per second, traveling across the gulfs between galaxy clusters takes billions of years. The expansion of the universe itself is, in many ways, working against us, stretching the space between us and the Great Attractor faster than our local gravitational pull can overcome. We may never, in any meaningful sense, actually reach the Great Attractor, but we are nonetheless falling toward it, always falling. As long as we exist, as long as galaxies exist, this gravitational dance will continue. So when you go outside tonight and look up at the stars, I want you to think about this. The ground beneath your feet, the air around you, every cell in your body is participating in a vast cosmic motion. We are being carried, all of us, towards something massive, something hidden, something that has been pulling us for billions of years and will continue to pull us for billions more. And the most remarkable thing about it, the thing that I think genuinely deserves your awe, is that we have figured this out. Without ever leaving the surface of our small planet, we have measured the gravitational pull of structures hundreds of millions of light years away. We have charted our motion through the cosmos with precision. We have, in a real sense, oriented ourselves in the vastness of the universe, identified our heading, recognized our destination. But we have not yet seen what's at that destination. We have not yet fully identified what is pulling us. And until we do, the title of this discussion will remain accurate. We can't see what it is. The cosmos has, for now, retained one of its most profound mysteries. In part 2, I want to take you deeper into the modern understanding of this puzzle. I want to talk about a remarkable discovery made just in the last decade that has expanded our picture of the cosmic landscape in ways that earlier astronomers could not have imagined. I want to talk about superclusters as actual physical objects with boundaries and structures and identities rather than just statistical groupings. I want to introduce you to a structure we now call Laniakea, which is the home address of our Milky Way, in a sense more profound than any previous map could provide. And I want to begin to talk about what the discovery of these structures means for the deeper question of dark matter, of cosmic flows, and of the nature of gravity at the largest scales. Because the universe, as we've been discovering over the last several decades, has a structure at the very largest scales that we are only beginning to comprehend. There are walls of galaxies. There are vast voids. There are filaments stretching across hundreds of millions of light years, connecting clusters and superclusters in a great cosmic web. And our motion, the pull of the Great Attractor on our galaxy, is itself just one note in a much larger symphony of cosmic flows, a symphony whose full structure we are still, even now, working to map. So when you go outside tonight, when you find a dark place and look up at the stars, I want you to think about everything we've covered. I want you to think about the layers of motion you're participating in. I want you to think about the Great Attractor sitting hidden behind the zone of avoidance, drawing your galaxy and you with it across the void. And I want you to think about the fact that even right now, even as you stand there looking up, you are moving. We are all moving. The entire cosmos is in motion, in flows and currents and tides whose full nature we are only beginning to understand. So we'd arrived at this point where our galaxy, the Milky Way, is being pulled across the cosmos at 600 kilometers per second. And even after identifying the Norma cluster and the more distant Shapley supercluster, there remained a residual mystery. The pull wasn't fully accounted for. Something else, something we couldn't quite see, was contributing to the gravitational tug on our entire neighborhood. And the question we left hanging was, what is the larger picture? What kind of cosmic structure are we actually embedded in? And what does our motion through this structure tell us about the nature of the universe? To answer those questions, I need to take you to a discovery that, when it was announced in 2014, fundamentally changed our sense of cosmic geography. It changed our address. Up until that point, when astronomers thought about where the Milky Way lived in the universe, they had a kind of hierarchy. We belong to the local group, which is a small collection of galaxies, including ourselves and Andromeda and a few dozen smaller companions. The local group is part of the Virgo supercluster, which is a larger collection of galaxy groups centered on the Virgo cluster, about 60 million light years away. And the Virgo supercluster was for a long time considered our home address, our cosmic neighborhood, the largest structure to which we, in any meaningful sense, belonged. But in 2014, a team of astronomers led by Brent Tully at the University of Hawaii published a paper that changed all of that. They had developed a new way of mapping cosmic structure. Instead of just looking at where the galaxies are, which is what we'd traditionally done, they looked at how the galaxies are moving, they mapped the cosmic flows, they asked the question, in every direction, where are the local galaxies being pulled to? And by following the flows, by tracing the gravitational currents that carry galaxies through space, they could identify what they called basins of attraction, regions of the cosmos where all the galactic motion converges toward a common point, regions that are, in a real sense, gravitationally bound, even if their individual components are too far apart to ever physically meet. What Tully and his colleagues found when they mapped these flows was extraordinary. They found that the Virgo supercluster, which we thought of as our home neighborhood, was not actually a self-contained gravitational unit. It was instead just one lobe of a much larger structure, a structure whose flows converged on a single basin of attraction. a structure that extended over 500 million light years across, contained roughly 100,000 large galaxies, and weighed in at about 100 million billion solar masses. They named this structure Laniakea, which is a Hawaiian word meaning beautifully immeasurable heaven. And the center of Laniakea, the gravitational basin into which all of its flows converge, is exactly the location we've been talking about, the Great Attractor region, the mysterious gravitational sink behind the zone of avoidance. We don't just live in a galaxy. We don't just live in a galaxy group or even a galaxy supercluster in the traditional sense. We live in Laniakea, a vast assemblage of galaxies all falling in their various paths toward a common center. And that common center is the destination we've been heading toward all along. I want to pause and let that sink in, because it's a genuinely transformative way of thinking about our cosmic situation. We belong to a structure, a definable, mappable, named structure. Laniakea has a shape. It has boundaries. On the far side, opposite from us, it borders other superclusters, the Perseus-Pisces supercluster, the Coma supercluster, the Shapley supercluster, which we discussed in part 1. And the boundaries between these superclusters are not arbitrary lines drawn on a map. They're real in a meaningful sense. They mark the places where the gravitational flows divide, where galaxies on one side flow toward Laniakea's center, and galaxies on the other side flow toward someone else's center. The cosmic landscape, in other words, is divided into watersheds. Just like rivers on Earth flow toward the sea according to topography, galaxies in the cosmos flow toward gravitational centers according to the topography of mass distribution. And we are part of one such watershed. We belong to the Laniakea drainage basin. Now, the wonderful thing about this picture is that it gives us, for the first time, a real sense of our cosmic context. When you ask the question, where does the Milky Way live? The answer used to be either too small a galaxy in the local group or too vague somewhere in the cosmic web of large-scale structure. With Laniakea, we have a meaningful, well-defined answer. The Milky Way lives in Laniakea. We are an outlying suburb sitting on one edge of an enormous cosmic structure, and we are slowly drifting toward its center. But here's where the story gets even more interesting. Because Laniakea, despite its enormous size, is not just floating in empty space. Beyond its boundaries, in every direction, lie other superclusters, and these neighboring structures exert their own gravitational influence on us. We are not just being pulled inward toward the center of Laniakea. We are also being pulled somewhat toward Shapley, which lies beyond Laniakea's boundary on one side. We are being pushed, you might say, away from the great cosmic voids that lie on other sides. And this brings me to one of the most surprising discoveries about cosmic flows, because it turns out that in addition to gravitational pulls from massive structures, there are also what astronomers have started calling repulsive flows, or more poetically, gravitational pushes. They arise from the great voids in the universe, from the vast empty regions where there are very few galaxies. How does emptiness push us? Well, here's the key. The empty regions don't actually push in the strict physical sense. Gravity, only attracts. It doesn't repel. But if you're located in a region with massive structures on one side and a great void on the other, the gravitational pull from the massive side dominates, and you end up moving in net away from the void. It looks, from your perspective, as if you're being pushed away from the empty region, but really you're just being pulled toward the matter on the other side. This effect, this apparent pushing from voids, has been mapped in recent years. There's a structure called the dipole repeller, sitting roughly opposite to the Great Attractor on the sky. It's a region of relative emptiness, a vast underdense area, and our motion through the cosmos appears to be partially driven by being, in effect, pushed away from this void while being pulled toward the Great Attractor on the opposite side. The combination of these effects, the push from emptiness and the pull from massive structures, gives us the net motion we observe. So now we have an even richer picture of what's going on. The Milky Way is not just being pulled by one thing, it's being acted on by the entire cosmic landscape around it. Massive structures on one side, empty regions on the other. Our motion is a complex result of all these influences, integrated over hundreds of millions of light years of cosmic geography. But, even this enriched picture doesn't fully account for the data. There's still a residual mystery. There's still something we haven't fully identified. Because when astronomers carefully account for all the visible matter, we can map every galaxy, every cluster, every supercluster, every void. The gravitational picture still doesn't quite add up. There is, when we do the math, a need for more mass than we can directly see, more gravitational influence than the visible structures can provide. The pull on our galaxy is, by some measurements, larger than the visible matter in our cosmic neighborhood can explain. And this brings us to the deeper question, the question that, has been hovering in the background throughout this entire discussion. What is the dark matter doing? Let me back up and explain what I mean. We know with extraordinary confidence that the universe is filled with a substance we call dark matter. Dark matter is not just a theoretical possibility. It's something we have multiple independent lines of evidence for. The motion of stars within galaxies tells us about it. The rotation curves of galaxies, the way stars at the outer edge of a galaxy orbit much faster than they should, if only the visible matter were generating the gravity, those rotation curves require enormous amounts of additional invisible mass. The gravitational lensing we observe around galaxy clusters, where the bending of light is much greater than the visible mass could produce, requires dark matter. The patterns in the cosmic microwave background, that ancient radiation from the Big Bang, require dark matter to explain how galaxies could have formed in the first place. Every line of evidence points to the same conclusion. About 85% of all the matter in the universe is dark, invisible, detectable only through gravity. We don't know what dark matter is in the deepest sense. We have hypotheses, weakly interacting massive particles, axions, primordial black holes, various exotic possibilities, but we have not yet directly detected the dark matter particles themselves. We know they're there, we know they have mass, we know they cluster together gravitationally, but the actual identity of dark matter remains, as of this moment, one of the great open questions in physics. And here's the connection to the Great Attractor story. The mass that's pulling our galaxy across the cosmos is not primarily the visible matter in the structures we've mapped. The visible matter, the stars and gas and dust we can see with our telescopes, is only about 15% of the total mass in any large structure. The other 85% is dark matter. So when we talk about the Norma cluster, or the Shapley supercluster, or Laniakea, or any of these enormous structures, what we're really talking about is enormous concentrations of dark matter with smaller amounts of visible matter clustered within them. The galaxies we see are like, glittering ornaments on a much larger invisible structure. The dark matter is the framework. The visible matter is the decoration. This is why the gravitational pull on our galaxy is so much larger than the visible mass would suggest. We're not being pulled by the galaxies we can see. We're being pulled by the dark matter that surrounds and contains those galaxies. The Great Attractor is not, in the deepest sense, a cluster of bright objects we just need better telescopes to see. The Great Attractor is predominantly a vast invisible concentration of dark matter, with some visible galaxies marking its location, but representing only a small fraction of its actual mass. So now we can return to our title question with a more sophisticated answer. Why can't we see what's pulling us? Well, partly because of the zone of avoidance, which obscures the visible matter in that direction, but also, more fundamentally, because most of what's pulling us is intrinsically invisible. Dark matter, by its very nature, does not emit or absorb light. It's transparent. It's, ghostly. You could be sitting in the middle of an enormous concentration of dark matter and you wouldn't see anything. The only way you'd know it was there is by measuring its gravitational effects. And that's exactly what we're doing. By measuring the motion of our galaxy, by tracing the cosmic flows, by mapping the gravitational pulls and pushes that act on us, we are doing dark matter cosmography. We are mapping the invisible architecture of the universe through its effects on the visible objects within it. The cosmic flows are, in a real sense, our best window into the distribution of dark matter at the largest scales. This is, I think, one of the most beautiful aspects of modern cosmology. We have learned how to see the unseeable. We have developed techniques for mapping invisible structures through their gravitational influence. The Great Attractor, in this view, is not just a curiosity, not just a puzzle, but a probe, a way of investigating the dark side of the universe, a way of constraining theories about dark matter and gravity and the large-scale structure of the cosmos. And the more we map, the richer our picture becomes. In recent years, astronomers have been extending these surveys further and further out, mapping cosmic flows on ever larger scales. The Cosmic Flows Project, led by the same Brent Tully who identified Laniakea, has now released maps showing the motions of tens of thousands of galaxies extending out to about 600 million light years. We can see how galaxies are moving across enormous regions of the cosmos. We can trace the great currents that carry galaxies toward concentrations of mass and away from voids. We can identify with increasing precision the locations of the dark matter that's driving these flows. And as we extend the maps further, we find more structure, more superclusters, more voids, more walls of galaxies. The universe at the largest scales is not smooth. It is dramatically structured, organized into a vast cosmic web of filaments and voids, with galaxies clustering along the filaments and avoiding the voids. The structure has names: the Sloan Great Wall, the Hercules Corona Borealis Great Wall, the South Pole Wall, which is a recently discovered structure stretching 500 million light years across the southern sky. Each of these is a tremendous concentration of matter, both visible and dark, that contributes to the gravitational landscape we're embedded in. But here's the thing. Even with all this mapping, even with all these surveys, the cosmos still has surprises in store. The dipole anisotropy of the cosmic microwave background, which is one of our most precise measurements of how we're moving through the universe, still has a slight discrepancy with the predictions based on the visible matter we can map. There's still a small residual pull that isn't perfectly accounted for by Laniakea, Shapley, and the other structures we've identified. Either there's more dark matter out there than we've yet mapped, or there's some subtle aspect of the cosmic flows that we don't yet fully understand, or, possibly something more fundamental is going on. Some researchers have, in recent years, started asking even more provocative questions. Is our understanding of gravity itself complete at the largest scales? Could the apparent need for dark matter be a sign that Einstein's general relativity, while spectacularly successful at solar system scales, requires modification at galactic and cosmic scales? There's a school of thought called modified Newtonian dynamics, or MOND, that suggests just this. And while MOND has its own difficulties accounting for many observations, the fact that serious physicists are considering modifications to our most successful theory of gravity tells you something about the state of the puzzle. We genuinely do not know with certainty that the standard picture is correct. Other researchers have suggested that the residual flows might reveal something about the very largest scales of the universe. Could there be structures even beyond what we've mapped, beyond the limits of our current surveys, contributing to the pull? Could the apparent direction of our motion through the cosmos tell us something about the geometry of the universe itself? Could there be, in the deepest sense, a preferred direction in the cosmos, a kind of cosmic axis that we're picking up on? Most of these speculations are, almost certainly wrong. The standard cosmological model, with its dark matter and dark energy and ordinary general relativity, is extraordinarily successful. It explains an enormous amount of data with remarkable precision. The residual mysteries are most likely going to be resolved by better mapping, better measurements, and a deeper understanding of structures we've already identified. But the fact that the mysteries exist, the fact that the data doesn't perfectly close, is a reminder that our picture of the cosmos is still under construction. And now I want to come to something that I think really brings this home. Because so far we've been talking about the Great Attractor and the cosmic flows and the structure of Laniakea in fairly abstract terms. Let me try to make it concrete. Let me try to give you a sense of what our motion through the cosmos actually means on a personal level. Imagine you could pause time. Imagine you could, freeze the universe in its current configuration and then step back and look at it from outside. What would you see? You'd see the Milky Way, our home galaxy, suspended in space along with all the other galaxies of Laniakea. You'd see Andromeda, our great companion galaxy, hanging nearby in the local group. You'd see the Virgo cluster, the central concentration of the supercluster we used to call home, glittering with thousands of galaxies. You'd see the various cosmic flows, the streams of galaxies that converge toward the Great Attractor region. You'd see the boundaries of Laniakea marking where our cosmic watershed ends and others begin. And you'd see, in the distance, the even larger concentrations beyond our boundaries, Shapley to one side, the Coma cluster to another, the Perseus-Pisces region to yet another. Now press play. Let time start running again. What happens? Everything starts to move. The galaxies in Laniakea drift toward our shared center. The visible matter shifts position. Streams of galaxies flow along filaments of dark matter. The whole structure breathes and evolves on timescales of billions of years. And our Milky Way is part of this great cosmic dance. We are not stationary. We are not isolated. We are flowing with our neighbors toward our shared cosmic destination. But the destination, you have to understand, is not really a destination in the way we usually think of one. Because the universe is expanding, the space between the most distant structures is stretching faster than the gravitational pull can overcome. So while we are falling toward the Great Attractor region in some local sense, the overall expansion of the cosmos is simultaneously pulling everything apart. The Shapley supercluster, for instance, is receding from us due to the cosmic expansion, even as it pulls on us gravitationally. The net result is that we may never actually reach it. We may, in some sense, be eternally falling without ever arriving. This is a strange and somewhat melancholy aspect of the cosmic flows. The gravitational pull is real, the motion is real, but the journey, in the deepest sense, is incomplete. The cosmos is expanding faster than gravity can pull things together at the largest scales, and as the expansion accelerates, which it appears to be doing, driven by the mysterious dark energy that pervades all of space, the situation gets even more pronounced. Distant structures will eventually recede beyond our cosmic horizon. The Great Attractor itself, billions of years from now, may become invisible to future astronomers, carried away by the expansion of space. So our motion toward the Great Attractor is, in a real sense, a snapshot of a particular cosmic moment. It's something we can observe and measure right now in our cosmic epoch, but it's not necessarily a stable, eternal trajectory. The cosmos is dynamic. The cosmic flows themselves evolve over time. And the structure of Laniakea, while real and well-defined for our purposes, is itself just a moment in the long evolution of the universe. Now I want to take you, in the final part of our journey, to the deepest implications of all of this. I want to ask the question that, I think is the most important one. What does this all mean for us? What does it mean to live in a universe with this kind of structure, with this kind of motion, with this kind of architecture? What does it mean that we are participants in cosmic flows, drawn by invisible forces, falling toward destinations we cannot fully see? And what does it tell us about our place in the cosmos, about the limits of our knowledge, and about the future of the universe we inhabit? But before we get there, I want to address one more puzzle that has emerged from this story in recent years. Because just when astronomers thought we were starting to get a handle on the cosmic flows, just when the picture of Laniakea and the Great Attractor seemed to be settling into a coherent framework, a new set of observations has, complicated things. A set of observations that suggests that our motion through the universe might be even stranger than we've been discussing. There's a measurement that astronomers refer to as the bulk flow. It's the average motion of all the galaxies in a large region of space relative to the cosmic microwave background. If our standard picture of cosmology is correct, the bulk flow should decrease with distance. As you average over larger and larger regions, the local effects of nearby concentrations of matter should wash out, and the bulk flow should approach zero. The universe, at the very largest scales, should be at rest relative to the cosmic microwave background, on average. But several recent measurements, using different techniques and different samples of galaxies, have suggested that the bulk flow at large distances is not zero. It's larger than it should be, larger than the standard model predicts. The galaxies in a vast region around us appear to be moving coherently in a common direction at a speed that is, hard to explain with the structures we've mapped. Now, these measurements are controversial. Different groups using different techniques sometimes get different answers. The samples are limited, the measurement uncertainties are large, and the standard model could still be correct. But the persistent hints, the lingering suggestion that there might be a large-scale coherent flow that we can't fully account for, is one of the active areas of cosmological research right now. What could cause such a flow? Well, one possibility is just that we haven't mapped far enough out yet. There could be structures beyond our current surveys, hundreds of millions or even billions of light years away, that are influencing our motion. We are, in a real sense, looking at the universe from inside a limited bubble of observation, and structures beyond the bubble could exert influences that look mysterious from inside. As surveys extend further, this kind of anomaly should either disappear as the structures get identified or persist, suggesting something more profound is going on. Another possibility, more speculative but more interesting, is that the bulk flow could be telling us something about the initial conditions of the universe, about the very moment of the Big Bang. Some models of cosmic inflation, the rapid expansion that took place in the first tiny fraction of a second after the Big Bang, predict that the universe might have a slight overall coherent motion that's been built in from the very beginning. If true, this would be a kind of fossil from the earliest moments of the cosmos, encoded in the motion of galaxies billions of years later. And there are even more exotic possibilities Some theorists have suggested that the bulk flow could be a signature of what they call dark flow, a coherent motion driven by mass concentrations beyond the observable universe, beyond the cosmic horizon, beyond the limit of what we can ever, in principle, see. In this picture, our universe is being pulled by something that lies outside of it, something we can never observe directly, something that might be evidence of a multiverse, of parallel universes whose gravitational influence reaches across the boundary into our own. These ideas are speculative. They are not, the consensus view, and most of the discrepancies that have been claimed have alternative explanations within the standard model. But the very fact that astronomers are seriously discussing these possibilities, that they are willing to consider the idea that we might be pulled by structures beyond our cosmic horizon, tells you how rich and how open the puzzle remains. So let me leave you for now with this. We have made enormous progress in understanding our cosmic motion. We have identified the major contributors to the pull on our galaxy. We have mapped the structure of Laniakea. We have charted the cosmic flows out to hundreds of millions of light years. But the puzzle is not yet closed. The exact nature of what's pulling us, the full accounting of all the gravitational influences acting on the Milky Way, remains incomplete. There is still mystery, there is still uncertainty, there is still, in the truest sense, something out there that we cannot see. And in part 3, I want to bring all of this home. I want to ask what it means for us as conscious beings on a small planet to live in a universe of such cosmic flows. I want to talk about the future of our motion, about what happens to the cosmic flows as the universe continues to expand and accelerate, about the ultimate fate of our journey toward the Great Attractor. And I want to come, in the end, to what I think is the most profound implication of all, which is the way these observations reframe our sense of our place in the universe. Because here's the thing, when you look up at the stars at night, you're not just looking at a pretty arrangement of distant suns. You are looking out across a cosmos that is dynamic, structured, and in motion. You are participating in flows whose origins lie in the earliest moments of the universe and whose destinations lie in epochs we will never witness. You are, in the most literal sense, on a journey through space, across time, towards something the cosmos has not yet revealed to us. So when you go outside tonight and look up at the stars, I want you to feel that motion. I want you to feel the spin of the Earth, the orbit around the Sun, the journey around the galactic center, and the great flow of the Milky Way through Laniakea toward the Great Attractor. Feel all of it. Feel yourself moving with the cosmos toward a destination we are only just beginning to understand. So we'd arrived at this remarkable point where our entire understanding of where we live in the universe had been transformed. We are not just citizens of the Milky Way, not just members of the local group, not just inhabitants of the Virgo supercluster. We are part of Laniakea, this vast assemblage of 100,000 galaxies all flowing toward a common gravitational basin. And we are being pulled simultaneously by influences from beyond Laniakea, by the Shapley supercluster on one side, by the dipole repeller on the other, by structures we are only beginning to map, the cosmic flows that carry us. They're not just simple motions toward a single point. They are a complex dance of gravitational pulls and pushes integrated across hundreds of millions of light years of cosmic geography. But I left you with a question that I want to take up now in this final part of our journey. What does it all mean? What does it mean for us, conscious beings on a small planet circling an ordinary star, to live in a universe of such cosmic flows? What does it mean that we are, right now, being carried toward destinations we cannot fully see, by forces we cannot fully identify, on timescales we cannot fully comprehend? To answer that, I want to take you forward in time. I want to project what we know about the cosmic flows into the future and tell you what astronomers expect will happen over the coming billions of years to the structure of our cosmic neighborhood and to our journey through it. And here's where, the story takes a turn that I find genuinely poignant. Because you see, the cosmic flows we've been discussing are not eternal. They're not stable features of the universe that will continue indefinitely. The cosmic flows are, in fact, a passing moment in the long evolution of the cosmos. And the reason has to do with one of the deepest mysteries in modern physics, the mystery of dark energy. Let me back up and explain. In 1998, two independent teams of astronomers made a discovery that revolutionized our understanding of the universe. They were studying distant supernovae, using them as cosmic distance markers, trying to measure how the expansion of the universe had changed over time. The expectation going in was that the expansion would be slowing down. After all, the universe is full of matter, and matter exerts gravitational pull, and that pull should be acting as a brake on the cosmic expansion. The question was just how much the expansion had decelerated. But that's not what they found. They found, instead, that the expansion was speeding up. The universe was expanding faster now than it had been billions of years ago. Some mysterious influence pervading all of space was accelerating the cosmic expansion. We call this influence dark energy. We do not know what it is. We have hypotheses, vacuum energy, quintessence, a cosmological constant, modifications of gravity, but the deepest nature of dark energy remains in some ways an even greater mystery than dark matter. We know it exists. We know it makes up about 68% of the total energy content of the universe. We know it's driving the accelerating expansion, but what it actually is, we don't know. For our story, here's why dark energy matters. Dark energy is winning. The accelerating expansion is, in the long run, going to overcome the gravitational attractions that bind structures together at the largest scales. Right now, gravity still dominates within structures like Laniakea. The galaxies in our supercluster are bound to each other gravitationally. They are not in net expanding away from each other. They are flowing toward the Great Attractor. But beyond Laniakea, beyond our local gravitational binding, the cosmic expansion is taking over. The Shapley supercluster, which I mentioned in part 1 as being a major source of the gravitational pull on us, is 650 million light years away. At that distance, the expansion of space is already faster than the gravitational attraction can overcome. We will never reach Shapley. Even though we are, in some sense, being pulled toward it, the cosmos is pulling us apart faster than gravity can pull us together at that scale. The space between us and Shapley is growing. And here's the truly remarkable thing. As dark energy continues to accelerate the expansion, this effect will spread inward. Structures that are currently weakly bound will become unbound. Galaxy clusters that are currently in the process of merging will be pulled apart by the accelerating expansion. Eventually, in the deep future, even superclusters like Laniakea will lose their coherence. The cosmic flows we've been measuring, the great currents that carry galaxies toward the Great Attractor, will slow, stop, and reverse. Galaxies that are now flowing toward each other will in time begin to flow away from each other, carried by the relentless expansion of space. In the very long term, billions and billions of years from now, the only structures that will remain gravitationally bound are individual galaxy groups. Our own Milky Way will eventually merge with Andromeda, forming a single massive galaxy that some astronomers have nicknamed Milkomeda. That merger will happen in about 4 billion years, which is, a long time, but a tiny fraction of cosmic history. And the merged Milkomeda will, along with a dozen or so other galaxies of the local group, eventually merge into a single elliptical galaxy. That will be our gravitational island, our cosmic life raft. The only thing that will remain together against the accelerating expansion of the universe. Beyond that, everything else will be lost. The Virgo cluster will recede from us. The galaxies of Laniakea will recede from us. The Great Attractor itself, the very thing we're now falling toward, will eventually become invisible, carried away by the expansion of space. Future astronomers, billions of years from now, looking up at the night sky from some descendant of Earth, will see only the merged remnant of our local group. They will not see other galaxies at all. The cosmic flows, the great currents we've been mapping, will have ceased entirely. You see why I find this story so poignant? We are living in a special moment in cosmic history, a moment when the structures of the universe are still coherent, a moment when the cosmic flows still operate, a moment when we can look out across hundreds of millions of light years and map the architecture of mass that's pulling on us. Future civilizations, if any exist, will not have this view. They will be cosmologically isolated, with no way to even know that other galaxies once existed beyond their local group. We, in this sense, are unbelievably fortunate. We are living during the period when the universe is, knowable, when its structure is visible, when the cosmic flows can be measured, when the relationship of our galaxy to the larger cosmos can be traced. And the very fact that we have figured all this out, that we have mapped these structures and identified the Great Attractor and named Laniakea, is itself a remarkable testament to what's possible during this brief window of cosmic transparency. Now I want to talk about what the cosmic flows tell us more deeply about our place in the universe, because I think there's something genuinely profound here. Beyond the specific facts and figures, here's what I mean. For most of human history, we thought of ourselves as static observers. We were here on Earth looking out at a universe that was, in some sense, separate from us. The cosmos was the thing we observed. We were the thing observing it. The relationship was, fundamentally one of separation. We were inside, looking out. But the cosmic flows tell us something different. They tell us that we are not separate from the cosmos. We are participants in it. The same forces that move galaxies move us. The same gravitational currents that carry the Milky Way across the universe carry our solar system, our planet, and us. When you stand outside tonight and look up at the stars, you are not just observing the universe, you are flowing through it. You are participating in motions that involve every atom in your body, every breath you take, every thought you think. The boundary between you and the cosmos is, more permeable than we usually realize. And the motion itself, when you really sit with it, is humbling. 600 kilometers per second. 600 kilometers every second, every moment of every day. Right now, as you listen to my voice, you are being carried that distance in the time it takes me to say a single word toward the Great Attractor, toward a destination you will never reach, toward an unseen source of gravitational influence that is, at this very moment, pulling on every atom in your body. There's a kind of grandeur in this, a kind of cosmic dignity. We are not, sitting still while the universe goes about its business around us. We are part of the business. We are caught up in the great flows of cosmic gravity. We are, in the deepest sense, ingredients in the dynamic structure of the universe. But there's also, I think, a kind of humility in this, because the cosmic flows remind us how much of the universe lies beyond our direct experience. We feel still, we feel local, we feel embedded in our small daily lives, on our small planet, with our small concerns, and all of that is real. All of that matters. But it is also embedded in a much larger context, a context we mostly cannot perceive, a context that is moving us all toward destinations we cannot see. The Great Attractor, in this sense, is a kind of metaphor for everything we do not know. It is a stand-in for all the cosmic forces that act on us without our awareness. It is a reminder that the universe is much larger and much stranger than our immediate experience suggests. And the fact that we have detected it, that we have measured its pull, that we have mapped its approximate location, is one of the great achievements of the human intellect. We have, in a real sense, used our small minds to grasp something enormous, something that in any earlier era of human history would have been completely beyond our ability to perceive. Now let me come, in these final moments, to a few thoughts that I think pull everything together. The first is about the nature of scientific inquiry itself. The story of the Great Attractor is, in many ways, a perfect example of how science actually works. We didn't set out to discover an enormous concentration of dark matter behind the zone of avoidance. We didn't, plan to identify Laniakea. We started with simple observations. We measured the motions of galaxies. We compared them to predictions. We noticed discrepancies. We followed the discrepancies wherever they led. And along the way, we discovered structures and phenomena that nobody could have anticipated. This is how the most important discoveries in science usually happen, not through some grand plan, but through patient observation, careful comparison, and the willingness to follow the data wherever it leads. The Great Attractor is real because the motion of our galaxy is real. The dark matter is real because the gravitational effects are real. We didn't invent these things. We discovered them by paying attention to what the universe was telling us, and the story is not over. The next decade is going to be transformative for our understanding of cosmic flows. New surveys, like the Square Kilometer Array Radio Telescope, the Vera Rubin Observatory, the Euclid Space Telescope, and others, are going to map the universe in unprecedented detail. We will get better measurements of cosmic flows. We will identify structures beyond Laniakea. We will, almost certainly find new puzzles, new anomalies, new questions to investigate. The story of the Great Attractor is not a closed chapter. It is an open one, with many more pages still to be written. The second thing I want to leave you with is a sense of the cosmic timescales involved. We've been talking about motions and structures and flows that operate on timescales of millions and billions of years. The Milky Way has been falling toward the Great Attractor for much of its history. The flows of Laniakea have been operating since the universe was less than half its current age. The merger with Andromeda is 4 billion years away. The dissolution of the cosmic flows by dark energy is many billions of years beyond that. Our own lifetimes in this context are vanishingly brief. The motion of our galaxy across the cosmos doesn't depend on what we do or don't do in the next century. The Great Attractor will continue to pull on us long after our civilization has, run its course. The cosmic flows are indifferent to human history. But here's the thing that I think is genuinely beautiful about this. The indifference of the cosmos to our existence does not diminish us. It puts us in context. It reminds us that we are, in some sense, witnesses to a much larger story. A story that began with the Big Bang, that has unfolded over 13.8 billion years, and that will continue for hundreds of billions of years more. We get to be present for one small chapter of this story. One small moment. And in that moment, we get to understand. We get to know. Think about what an extraordinary thing that is. The cosmos doesn't need us. The Great Attractor doesn't care whether we exist or not. The cosmic flows would carry us along whether or not we ever noticed them. But we did notice. We figured it out. We measured the motions, we mapped the structures, we identified the pull. And now we know, in a way that no civilization before us could have known, that our galaxy is being carried toward a mysterious destination in the depths of space, that knowing, that understanding is itself something precious. It is something the universe has not, granted to most of the matter that exists. Most of the matter in the cosmos is just matter. It doesn't know anything. It doesn't reflect on its motion or its situation. It just is. We, on the other hand, are matter that has organized itself in such a way that it can think about itself. We are matter that has become aware. And in that awareness, we have come to see the structures of the cosmos with a clarity that in earlier eras would have been considered impossible. This brings me to the third thing I want to leave you with, which is, the deeper meaning of the title of this discussion. We can't see what it is. We can't see with our eyes the dark matter that makes up most of the mass pulling on our galaxy. We can't see through our telescopes the regions hidden behind the zone of avoidance. We can't see, even with our best instruments, all the structures that might lie beyond our current cosmological horizon. There are aspects of the cosmos that are in deep and permanent ways beyond our direct perception. But this is not a failure. This is not a limitation that diminishes our knowledge. This is, in fact, an invitation. The unseen aspects of the universe are the ones that science exists to investigate. They are the puzzles that keep us asking, looking, building new instruments, developing new theories. The fact that we cannot see what's pulling us is, in this sense, what makes the question so worth asking. And here's what I want to say with as much emphasis as I can. The unseen does not equal the unknowable. The fact that we cannot directly perceive dark matter does not mean we cannot understand it. The fact that the Great Attractor is hidden behind the zone of avoidance does not mean we cannot map its location and constrain its mass. The fact that structures beyond our horizon will always be beyond our direct reach does not mean we cannot, through observation and theory, infer their existence. We are, in other words, in the business of seeing the unseen. We are, as a species, working out how to perceive the imperceptible. The Great Attractor is one of our most successful examples of this. We have, through gravitational influence alone, mapped a structure we cannot directly see. We have, through the motion of galaxies, identified a destination we cannot directly observe. We have, in a real sense, used the visible to reveal the invisible. This, I think, is one of the deepest things to take away from the story of the Great Attractor. The universe is not just the things we can see, it is also the things we cannot see. And the relationship between the visible and the invisible, between what we directly perceive and what we infer, is the very heart of how science works. The Great Attractor is a particularly dramatic example, but the same principle applies everywhere. The structures of matter, the laws of physics, the patterns of nature, they all have invisible aspects that we work with great effort to make visible through inference and measurement. So when I tell you that astronomers are terrified, when I use that word in the title of this discussion, I want you to understand what I mean. We are not terrified in the sense of being afraid of imminent disaster. We are not, predicting cosmic catastrophe. The pull of the Great Attractor poses no threat to Earth or to our civilization or to anything we care about on a human scale. The motion is slow. The destination is far. The effects on our daily lives are nil. But there is a kind of awe, a kind of vertigo that comes from really sitting with what the data tells us. There is a kind of disquiet that comes from recognizing that we are caught up in cosmic flows we did not choose, that we cannot stop, and that we cannot fully see. There's a kind of unease that comes from understanding that the universe is much stranger, much larger, much more dynamic than our daily lives suggest. And in that sense, yes, the contemplation of these cosmic motions can be, a humbling and even unsettling experience. The terror, if we want to use that word, is the terror of the sublime. The terror of recognizing that the universe operates on scales of size and time and energy that dwarf anything in our experience. The terror of realizing that we, with all our concerns and ambitions and beliefs, are riding along on a galaxy that is being pulled towards something we cannot fully comprehend. But the sublime, is not just terrifying, it is also beautiful. It is the kind of beauty that doesn't fit into easy categories, that doesn't conform to our familiar aesthetic frameworks, that requires us to expand our sense of what beauty can mean. The Great Attractor is sublime in this deeper sense. It is beautiful precisely because it is so vast, so mysterious, so far beyond our immediate experience. The fact that we can know about it at all, that we can measure its effects and ponder its nature, is itself something to celebrate. So let me come now to the very end of our journey together. Let me try to bring everything I've been saying back to where we started. In part one, I told you about the layers of motion you are participating in, ending with the discovery that our entire galaxy is moving at 600 kilometers per second toward a mysterious destination in the southern sky. In part two, I introduced you to the concept of Laniakea, the home supercluster we belong to, and to the cosmic flows that map the gravitational landscape of our local universe. And in this final part, I have tried to give you a sense of what all this means about our place in the cosmos, about the limits of our knowledge, about the future of our cosmic journey. The Great Attractor, in the end, is more than just an astronomical curiosity. It is a window into the deeper structure of the universe. It is a reminder that the cosmos is dynamic, that we are participants in its motion, that there is much more to reality than meets the eye. And it is, in a way, I find genuinely moving, a kind of cosmic mirror. Because when we look toward the Great Attractor, we are not just looking at something out there. We are looking at the source of our own motion. We are looking at the destination that, in some sense, defines our journey. We are looking at a piece of our own cosmic identity. We are the galaxy that is falling toward the Great Attractor. That is, in a real sense, who we are. Our cosmic identity is not just the Milky Way as a static collection of stars. It is the Milky Way as a moving structure, a structure with a heading, a structure participating in a great cosmic flow. To understand who we are, in the deepest cosmological sense, we have to understand where we're going. And where we're going, as it turns out, is towards something we cannot fully see. So when you go outside tonight, when you look up at the stars, I want you to remember everything we've covered. I want you to think about the rotation of the Earth carrying you eastward at 1,000 miles per hour. I want you to think about our orbit around the Sun, hurtling us through space at 67,000 miles per hour. I want you to think about the Sun's journey around the galactic center at 500,000 miles per hour. And I want you to think about the Milky Way's flight through Laniakea toward the Great Attractor at 1.3 million miles per hour. You are doing all of those things right now, at this very moment. You are participating in cosmic motions that span scales from the personal to the galactic to the supercluster. You are caught up in the great flow of cosmic gravity. You are heading towards something we cannot yet fully identify, something hidden behind our own galactic dust, something that is, in a real sense, drawing your entire civilization across the universe. And here's the thing I want you to feel, more than anything else. The motion is not a burden. The mystery is not a problem to be solved. The unseen forces are not threats to be feared. They are, all of them together, an invitation to wonder, an invitation to investigate, an invitation to be part of the long human conversation about what kind of universe we live in. We have, in our few thousand years of organized inquiry, gone from believing that the stars were fixed points to mapping the gravitational influence of structures beyond the horizon of visible light. That is, a staggering achievement, and the journey is not over. The next generation of astronomers, using instruments not yet built, will see things we cannot. They will map structures we have not identified. They will resolve mysteries we cannot solve. The story of the Great Attractor, of cosmic flows, of dark matter and dark energy, and the architecture of the universe will continue to unfold long after this conversation ends. But you, right now, are part of that story. By thinking about these things, by trying to understand them, by feeling the cosmic motion in which you participate, you are doing something that, no human being could have done even 100 years ago. You are perceiving, however dimly, the structure of a cosmos that operates on scales beyond our daily experience. And in that perception, you are participating in one of the deepest and most beautiful activities our species has ever undertaken. So look up tonight, look at the brightest stars you can see, and the dimmer ones, and the dark patches between them, and know that you are not just looking at the universe, you are flowing through it. You are being carried with every atom in your body toward a destination we cannot fully see by forces we are still learning to understand. The cosmos is in motion, and so are you. The Great Attractor is pulling, and you are responding. This is, in the deepest sense, what it means to be a small, conscious creature in a vast and dynamic universe. You are aware. You are moving. You are part of something so much larger than yourself that the very concept of self begins to dissolve into the cosmic flow. And in that dissolution, in that participation, there is, I think, a kind of meaning that no smaller cosmos could ever provide. The universe is calling us forward. The Great Attractor is pulling us on. The cosmic flows are carrying us toward whatever lies ahead. And we, in our brief and beautiful moment of awareness, are along for the ride. Thank you for joining me on this journey through the cosmic flows. Until next time, keep looking up. And remember, even when you're standing still, you are moving. The universe sees to that.